I'm Stephen Blackwood, and I have the great honor today to be here with Sir Roger Penrose and Dr. Jordan Peterson. Let's get right down to it. Jordan, I know you have questions you're keen to pose to Sir Roger. Over to you.
Yeah, well, I've wanted to talk to a theoretical physicist for about 30 years, and so I'm pretty happy that you're the theoretical physicist that I get to talk to.
I'm probably not representative, so you...
Well, that might be even better. So I want to jump right into it. A colleague and friend of mine is a AI engineer and a computer engineer, and he's built a lot of the world's great chips, iPhone chip, and first 64-bit chip, the Alpha, back in 1985. And we were having a conversation. I said I was coming to meet you, and that you, and I don't want to put words in your mouth, believe me, but that you believe that consciousness is in some fundamental sense non-computational. And I asked him what he thought about that, and part of the reason I asked him is because he's, of all the people I've ever met, and maybe of all the people in the world, he's the person who's done most to build arguably brain-like algorithmic systems. And so I asked him if he thought that there was a distinction between the algorithmic computation of cognition per se and whatever consciousness might be. And he thought it was algorithmic all the way down. And I understand that you don't believe that. I also went with him a couple of times to a consciousness conference in Tucson where Hameroff spoke.
Sure.
So we got familiar with that line of reasoning. And I also understand, I believe, that part of the reason that you think that consciousness is necessarily non-computational is because of Gödel's theorem. And so maybe we could enter there. So I'm very curious about your proposition that consciousness per se is non-computational, and I'm curious about why you came to that conclusion, and if you think that's a warranted conclusion, what you think about that in relationship to these complex AI systems, and also in relationship to Gödel's theorem.
Well, I've never seen the argument refuted. I've just talked to people who've never really understood it, as far as I know. No, the argument goes back to when I was a graduate student, and I was doing pure mathematics, algebraic geometry, and I went to 3 courses, which were nothing to do with what I was supposed to be doing. One of them was a wonderful course by Hermann Bondi on general relativity, which had a big influence on what I did later on. One was a talk by the great physicist Paul Dirac, and that taught me about quantum mechanics. And the third one was a course by a logician called Steen, and he taught me about Turing machines, the notion of computability, what it is and how you understand that, and the Gödel theorem. And I had heard vaguely about the Gödel theorem previously and had been rather worried because it seemed to show that there were things in mathematics that you couldn't prove. What I learned was that it's not like that at all. Well, it is like that in a sense. If you lay down the rules of what you call a proof, and if those rules are such that they could be checked by a computer, checked whether they've been correctly applied by a computer, so computational rules in that sense, then you can construct a sentence. This is what Gödel did, which by the way it's constructed, you can see that if you trust the rules, that is to say, if you believe that the rules do, if they say, yes, you've proved it, tick, then you believe it's correct. That is to say, if you have trust in the rules, that trust extends beyond the rules. In other words, you can see that a certain statement is true by virtue of your belief that the rules only give you truths. Yet, that statement is underivable, unprovable using the rules.
That statement of faith about the rules.
It's not a statement of faith. I'm sorry, I didn't understand. The faith it's not a faith. You understand the rules, you check them, you say, yes, that's okay. If that rule is correctly applied, I agree. It does. It's a rule which is within something that you believe to be appropriate. Yeah. And this rule, it's built up out of things like this, which nobody would dispute. You say, okay, if you follow those rules, and it says, yes, that's a proof, then you believe that the thing that it says, yes, it's a proof, is actually a true statement. So does a proof really mean that it's true? If you believe that that conviction that the proofs actually do what they're supposed to do gives you something beyond the rules themselves.
Okay, that's what I was referring to with this,
Yes.
with the word faith, is that the statement of
it's not-
belief.
no,
well, I
faith
shouldn't
is,
maybe
I
use
think,
that
the
word.
wrong word.
Well,
Yes.
I guess I'm
Okay,
wondering
yes.
what do you think it is that
Understanding.
constitutes that belief? Okay, and why the word understanding specifically? Because that's the thing in some sense that's outside the system. The understanding?
Yes, it is, because you can see it is, because it's the understanding that the rules give you only truths that enables you to understand that this Gödel statement is actually true.
And so is that belief in that truth of that proof, that is one of the things that Gödel pointed out would be necessarily outside any system that's both, formal, logical, and coherent?
It shows that I read it in this particular way. I don't think he said it quite like this, but I read it in the following way, that understanding, whatever that word means, is not computational.
Okay.
It's
so
not.
that is what
It's not the following of rules. It's something else.
Okay, so let me ask you a question about that. So this is a three-pronged question, let's say.
Okay. Yes.
It seems to me that there's a high probability that the future is actually indeterminately different than the present and the past, that it's actually unpredictably different.
Oh, this is a different question.
Yeah,
now you're talking about determinism.
Yes, but I think it seems to me that it's tied to this idea that computation can be complete and algorithmic. I don't think it can be, because if the future differs in a fundamental manner, an unpredictable manner from the present or the past, then a deterministic algorithmic system can't maintain a grip on the horizon of the future. And I have another part of that question.
But it's a different question. So I think it's important to distinguish these things.
Yes.
Because up to this point, I was not talking about indeterminism.
No.
I was talking about rules. Well, just yes or no, and I mean, it's not a question of maybe or. I mean, it isn't even talking about the laws of physics at this stage. That's the second step, if you like.
I guess I leapt
Yes.
forward to something like the potential necessary function of consciousness. So, because one of the things consciousness seems to do from a neurophysiological perspective, for example, we tend to become conscious of our procedural errors. And so consciousness becomes alerted to the errors and then zeroes in on the source of the error in some sense and corrects it. And so it looks to me like it's something like a correction system for underlying algorithmic systems. So, for example, if you practice a motor routine for a long time, you build specialized algorithmic machinery in your brain that runs it. But maybe you've put in an error. Maybe you're playing a difficult piano phrase, for example, and you stumble over a note. You've automatized that. You play it, and you listen, and you hear the anomaly, which is the error. Your consciousness focuses in on that. A large brain area will activate as a consequence of becoming aware of that error. Then when you practice the new routine that's corrected, the brain area will shrink and shrink and shrink until it's a small part of the brain, usually in the back of the left hemisphere. And now you've built another automated machine to play out that phrase. And consciousness, I think it was Whitehead who said that at least the purpose of consciousness, although he might have used thought, was to increase the number of things that we can do without consciousness or thought. But it seems to be this horizon phenomena. And the reason I was asking about the indeterminacy of the future was twofold, is that if the future is deterministic, then an algorithmic system could in principle adapt to it. But it doesn't seem to me that the future can be predictable, and I think that might be grounded in something like quantum indeterminacy, because there isn't a fundamental determinism that propagates all the way up. So,
Well, you see, I mean, we have to. The things I was talking about up to this point were not to do. They weren't even to do with the laws of physics, so that's a separate question. I mean, it did relate to that, which is my own views certainly did depend on that. But the question of determinism is a separate issue. And the normal way we look at quantum mechanics is it does involve an indeterminism, which you can have a theory which does that too. But that's different, you see. If it's just indeterministic, it's not connected. You see, the Gödel argument is to do with things where you have definite rules. You can check whether these rules have been followed or not, and the question is whether it coincides with your understanding about what things are true or false in mathematics. So that's what it's to do with. Now you see, you can question how you move from that into other aspects of what consciousness does. And also the question you were referring to is whether something's automatic, and a pianist can play things, and obviously where the little finger goes next is not something that he or she decides to do. It's all largely controlled by the cerebellum, probably, which, as far as we know, is entirely unconscious. So the greater number of neurons in the brain, which are in the cerebellum, seem not to be acting according to conscious actions at all. It's something completely unconscious.
Right. Well, yes, that's a very strange thing that, people make the case as well that there's some simple relationship between neuronal function and consciousness. But as you pointed out, the cerebellar activity doesn't seem to be conscious at all. And then there's a tremendous amount of neurons in your autonomic nervous system distributed throughout your body. And there may be some consciousness associated with that, but it's not particularly acute, and most of the time it's entirely unconscious. And the autonomic nervous system is running your digestive system and your heart and all of these inner automated systems. And it's interesting too, because often becoming consciously aware of a highly functional unconscious system actually impairs its function rather than improving it.
That could be, yeah, sure. I'm not quite sure what this tells us about consciousness. It just tells us certain things are not conscious, which are controlled by neurons in the brain, and so it's a different issue.
Right.
May I just jump in to ask Sir Roger if you would say a word or two more about why it is that consciousness cannot be reduced simply to mechanistic processes?
Well, you see, I'm very careful to say I'm not talking about consciousness in all its aspects.
Yes.
For example, I have nothing to say about the perception of the colour green, for instance. Sure, there's something going on which makes green have a certain impression on one. But this is not what I'm talking about. And probably most of the things that we think about when we talk about consciousness are not what I'm talking about. So I'm only talking about a very specific part of what consciousness does. And the argument is that if this is something which is not a computational process, then it sort of sheds a question mark on the whole thing. But it's only very specific to the question of understanding. So I tend to make that point clear. And understanding is something which, certainly in the normal usage of the word, implies conscious. You wouldn't say of a device normally that it understands something without it being aware of something. And aware means being conscious of it. So that's just normal usage, and I'm going along with that. So I don't know what most of these words mean, but I would say that understanding is something which requires consciousness.
Yes, is one way into this to speak about, so much of our thinking, of course, is calculative. There's a goal there. We're calculating how to get to it, so there's a huge amount of life that is like that. But to then ask the question about why this is a goal, or why this is worthy of being a goal, or what would make it worthy of being a goal, or what would make that worthy of being a justification for that to be a goal, the kinds of thinking that you have to engage in order to reflect upon the nature of the ends and purposes, is distinct from the kinds of thinking you engage in to calculate your way to a goal. And that seems to point towards the realm, or a kind of thinking or awareness that is clearly distinct from a simply mechanistic calculation.
Yes. I certainly wouldn't disagree with that. It's just it's hard to know whether those things could be put into a computational system. Mm-hmm. The reason for concentrating on this very specific area is that I can say something about it, that's all. Mm-hmm. So the particular area is mathematical proof. I see most people don't bother themselves with mathematical proof, and they're conscious too, so I'm certainly not saying that's an indicator of consciousness. I mean, I'm saying it is something which requires consciousness, but I completely accept that there are all sorts of other aspects of consciousness which are going on all the time and which are much more important. I've gone along with that too. But it's just that if you can find something in what consciousness seems to do, which is demonstrably not computational, that's saying something. And that's the limited little thing I'm trying to say.
Now, you started working with Hameroff, as I understand it, to try to provide something approximating a localization or a neurophysiological account of what this non-deterministic process might be. And
but I didn't say that's usually non-deterministic. That's different.
okay,
See, it's very easy to confuse the two.
well, and I am confused about them apparently.
Now, you see, non-deterministic means that rules don't have a clear statement about what happens next. And maybe there is a choice about what happens next. And that choice might be random, or maybe choice in some more personal sense that you have a reason. I don't know. But usually one talks about randomness there. You say that the theory does not have a complete description of what it tells you happens in the future, because there is a random element in it. And the way quantum mechanics...
Random element in the future.
in the future. That's what normally, the way in which one talks about quantum mechanics normally. I mean, I have...
Right. And that's a truly random feature, so it's not predictable.
In current quantum mechanics, that's correct, yes.
Okay, so that's what I was referring to when I was referring to the indeterminacy of the future horizon. It was that randomness that I was trying to point
Yes, but you see, I mean, but it is another question. You can have a random device which is otherwise computational. I mean, it just, you put in at certain points, okay, do something randomly. Thing is, I don't think, an interesting question there, I don't think that gives you anything in the way of establishing results which seem to be a non-computational process, like with the Gödel thing.
Okay, so there's an evolutionary answer to the problem of emergent randomness, and the answer is, so a mosquito's a good example.
Yeah.
Or fish, any animal that lays a tremendous number of eggs that could conceivably march to maturity. So there's genetic mutation in all, so maybe let's say, just for the sake of argument, that a given mosquito lays 1 million eggs, fertile eggs in its lifetime.
Yeah.
Now, there's variation in those mosquito patterns, and at least a certain amount of that variation is random. That's a consequence, and it's actually a consequence, I would say, of events that are actually manifesting themselves in some sense at a quantum level, because at least some of the mutations are caused by radiation, and so there's disruption at a molecular level, and so evolution seems to be able to use the admixture of randomness into structure as a means of dealing with the indeterminacy of the future. And to some degree it does that through death, right? Because of those 1 million mosquitoes, on average, only one manages to propagate itself to reproduction, or we'd be knee-deep in mosquitoes and like...
No, I understand what you're saying, yes. But what I'm trying to say is that what's going on with consciousness is different from that. Because I don't see how this, you putting randomness and in the way you're suggesting, and clearly that is an important aspect to evolution and so on. I certainly wouldn't deny that at all. But it's not the same thing. So that
consciousness isn't producing randomness in response to indeterminacy.
Yes, it's when I say non-computational, I don't mean that it's random at certain times. I mean something quite different.
So let's zero in on that. So, because I'm very curious about what you do mean. I mean, this is obviously a tremendously important distinction between the computational algorithmic domain and something that's in some sense outside of it. And I'm struggling to understand at the most detailed level, let's say, how you envision the structure and function of consciousness, or maybe just the function. It's not producing mere random variance, and that can't be, because random is too widespread. So at the very least, so for example, if you study creative people, we've done a lot of this, there's in some sense more randomness in their speech. Because imagine that if you utter a given word, there's a certain probability that another word will emerge in the field around that. The creative people use lower probability concepts and words in their approach. So there's a kind of randomness. They go farther out into the word association field, and that does help them generate more creative solutions. But that's not, if that becomes unconstrained to too great a degree, you get, well, maybe like a manic creativity that's counterproductive and too random. People are jumping too much from disconnected point to disconnected point. And so consciousness doesn't seem to be, creative consciousness doesn't seem to be a mere random walk. So that's a psychological take on that. But so what do you think, I'm still struggling to understand what you think consciousness does. It does understand.
Yes. You see, I think probably you're trying to make me be more specific than I can be, because I don't know what it is that, how to make a device that can understand something. So I'm just trying to say that whatever understanding is, it's not a computational process. And that's the argument I'm making.
Okay, I see.
No, it's not.
So you're not trying to specify what it might be. You're just saying it has to be something that's non-computational.
Yes, that's right. Yes.
Is there a fundamental link? I mean, when we say it is not non-computational, does that mean, or does that not mean, by definition, that consciousness in some deep level is free?
No,
It does not.
That's right. I'm not saying, I mean, these are open questions. I'm not saying that. I mean, maybe there is an aspect of indeterminism in it, and that could be. But that's not what I'm saying. And the trouble is, I think it's not a concept which people appreciate usually. So I can give you examples of non-computational things, and one of the examples I often give is if you imagine a pattern of squares, equal squares, or just a normal square array, and you can consider a finite shape made out of squares. I think it's called a polyomino, shape made out of squares. And if you're given a finite set of these polyominoes, and the question is, can you cover the plane with those shapes, only those shapes, no gaps, no overlaps? Now that question, the answer yes or no. The answer is definite yes or no. Either you can or you can't. But it's not an algorithmic process. It's shown mathematically that there is no algorithm which can tell you yes or no whether these shapes will cover the plane.
Okay, so when I was talking to my brother-in-law,
Yes.
I was talking to him about these AI systems
Yes.
that learn how to recognize, let's say, cats from photographs. He told me there is no way of algorithmically determining the program that the machine learning systems will eventually apply to the problem of identifying cats in a photograph. But if you let the AI neural networks run and then you analyze their output, you often get something that resembles an algorithmic program as an output that you could have hypothetically calculated if you could have specified the search space. It's something like that. But there's no way of doing that without letting the program do its walk through the domain of cat photographs with its differentially weighted neural network architecture. You can't a priori predict it.
Yeah, well, I still don't think it's the same thing. I could certainly give it different shapes, and you can say, tell the machine, which of these will tile the plane, which won't. Now, will that learn to give you correct answers?
Well,
Probably, usually it does.
I suppose once it's tiled, you could formalize the process by which it was tiled, right? Because you could describe the mechanisms or the order in which the tiles were located and the rotation of them. You could specify it after it had all been laid down. And I think that's analogous to what the AI systems seem to be doing when they're learning to perceive.
But the trouble is that it's not. The methods whereby you can tile the plane are I mean, just the theorems tell you that you can't put them on the computer. I mean, you might get the thing which works most of the time.
Right.
It's quite possible.
Well, so in those tiling problems that you're describing,
Yeah.
and so that is, I guess I kind of see why you're interested in the tiling issue. So that has to do in some sense with the ability to map a surface with a certain representational form. And so if you have these tiles that you described and you're trying to completely cover a given surface, that's a mapping problem. I see what you're doing with that. Are there different ways that you could conceivably solve that problem? So
Yes,
okay, so even if you do converge on a solution, you haven't converged on the only solution.
Oh, absolutely. I mean, there was an earlier result which showed that if it were true that any way of tiling that plane with these shapes, with, say, some given set of shapes, finite set of shapes, if it tiles the plane, you can do it periodically with a repeating pattern. If that were true, then there would be an algorithm. But it's not true, because there are certain ways of tiling a plane which do not
Have a repeating pattern.
have repeating patterns.
So now that's so cool, because I was wondering today, why in the world is he obsessed with tiles? What's going on? But, well, the fact that the tiles you're essentially mapping an area with a predetermined concept in some sense. That's the tile shape. And you said it can be non-repeating and still solve the problem.
You see the one in front of the mass building. That's an example. That's an example of a tiling set, only two different shapes there. I mean, these aren't polyominoes, but never mind about that. Those two shapes will tile right out to infinity. But there is no way of doing this which is periodic. And you can see, it's almost, you see this sort of repeats
So how
itself.
do people actually do it then?
Because there's another way of telling you how to do it.
with the tiling, so you designed the tiling in front of the building. So do you actually tell the workmen how to start the tile, and then how do they figure out how to do it?
They had a plan for the whole thing.
And you devised the plan for the whole thing?
Yes.
So you provided the map?
Yes.
Okay. How in the world did you get interested? Do you have any idea how you initially got interested in the tiling problem?
Yes. Well, you see, it certainly was this computability question. That is the connection, yeah. I had learnt, I think I'd seen an article in the maths reviews, this is reviews mathematical papers and so on, and I'd seen that somebody had produced a set of tiles which would tile the plane only in a non-periodic way. And I hadn't seen what they were like. And there was a conversation, I think it was just after I'd been appointed to my chair here, the Rice Bowl chair, but before I'd taken it up. And I had a conversation with an American mathematician, and he had told me in detail about, I think there's a mathematician called Raphael Robinson who had got the number down to 6, and he'd got a set of 6 tiles which would only tile the plane in a non-repeating way. And he said that Raphael Robinson, this was Simon Cochin, who's an American mathematician, and he said that Raphael Robinson was somebody who liked to get the number to the smallest number. He was sort of perfectionist in this way. And he said he's got this run. It started out with several thousand, you see, and he got it down to 6. And he's pretty pleased with that. And I said, well, I can do it with 5. I happen to know. I had a set with 6, you see, but I knew that I could reduce it to 5.
How did you know?
How did I know that
you could reduce it to 5?
Because the way that I mean, it's just a technical point. There was a certain shape for matching, and this shape only fitted into one other tile, so that I could glue the ones with. It's just a slight detail point. I could glue some of the tiles together to make them 5.
And when you're mapping the plane,
yeah,
do you map it to the precise borders of the plane, or can there be overlap? You know what I mean? Can it be messy on the edges, or are you trying to precisely cover, let's say, a rectangle?
It keeps on going beyond the edge, and then you cut it along the edge.
Yeah. Okay.
That's right. Yeah,
Okay.
Yeah.
Okay. So now you also had some interactions, at least at arm's length, with Escher.
Oh yeah.
So what I read was that you and your father had been interested in Escher's work, and you worked out with him the ever-ascending staircase, which, by the way, seems to me quite similar, especially to the music in Bach's Third Brandenburg Concerto, and I talked to a musician this week about how Bach managed to make this continual ascending spiral that never really goes up.
That's true. There is a thing like that. Yeah, right. Yes.
So, and then you sent the drawings of the staircase to Escher.
Well, the story was a little bit longer than that, because I had been at this. I was a graduate student, I think in my second year. I can't quite remember. And I and a colleague went to Amsterdam to go to the International Congress of Mathematicians, which happened every 4 years. And at this congress, I happened to see one of my lecturers, and he had a catalogue which had one of these Escher pictures on it. I said, what on earth is that, you see? And he said, well, this exhibition in the Van Gogh Museum by this artist, M.C. Escher. Never heard of him before. I went to see the exhibition. I was absolutely blown over by these pictures. One in particular, I think, was called Relativity. And I came away thinking, gosh, that's amazing. I wonder whether I could do something a little bit different that I hadn't actually seen in the exhibition. And so I tried to make a construction with bridges and roads going in possible ways. And I simplified it down to this thing that people refer to as a tribar.
I've seen the tribar.
And I showed my father. I mean, I didn't know that there's this Swedish artist called Oscar Reuterswärd who had done things very similar earlier. But Escher didn't know about him either. But anyway, and there are other artists who've done things like, if you look carefully in the old, there's a Bruegel which has a picture of gallows, and it's joined up differently in the top.
Yes, I've seen that picture.
Yeah. So there are other people who had played with these ideas, but I hadn't quite seen it in Escher. And so my father and I wrote an article. He developed this. The staircase was his, actually. Mm-hmm. He was designing buildings, and then he produced the staircase, which went round and round. And we decided to write a paper on this. We had no idea what the subject was, what journal did we send it to. So my father said, well, I happen to know the editor of the British Journal of Psychology, so let's call it Psychology. So we sent it to them, and they accepted it. He said he thought he could get the editor to accept it. They did, and we gave reference to the catalogue and to Escher's exhibition. And then my father had a correspondence with Escher, with letters going backwards and forwards. And then I think I was driving in the Netherlands for some other conference, I think. And I was curious, and when I was reasonably close to Escher, I phoned him up. I got the phone number from my father, and he was very nice, and he invited me and my then wife to tea, and I just had a chat with him, and he sat at one end of a long table, I was at the other end, and he had two piles of prints, and he said, well, this pile, I don't have many left, I'm afraid. And he pushed the other pile to me. Choose one. So I sort of went through these things, and I picked one out. Pretty hard to choose one out of all that. And I chose one called Fish and Scales, which he was actually rather pleased, because he said, well, most people don't understand that one. So I felt a bit flattered by that. But I then gave him a set of little pieces of just one shape, and I gave him a set of them and said, well, can you tile with those? And then a little while later he wrote to me and said he'd seen how to do it, but he wanted to know what the underlying principle was. So I did. I'm afraid I was a very bad correspondent. It took me a little while before I got back to him. But I showed him what it was based on, and on the basis of that he produced what I believe was his last watercolour, maybe his last picture as far as I know, a thing called Ghosts, which is based on this. It's the only tiling, as far as I know, that he ever did, which is what's called non-isohedral. You see, usually he did periodic ones, but they're periodic in the strong sense that if you find a shape, the next time you see it, it has the same relation to the pattern as a whole. So you could move this one into that shape, and the whole pattern goes with it into itself. But the one I showed him was what's called non-isohedral, that you can have different instances of the shape. So this one has a different relation to the pattern as a whole from that one. And so if I move this one into that, I can't bring the whole pattern along with it. So you have two different roles that the shape plays. And the last one of his pictures showed this.
So I'm curious too. So this about two things now. I'm interested in why you're so fascinated by the relationship of a geometric shape that can be arrayed in a variety of different manners to this underlying problem of mapping. So you're reducing or establishing a relationship between the problem of mapping a large terrain to the utilization of like very stringently defined, what would you call them, representational systems, or that's a geometric form. What is the geometric form conceptually in relationship to the problem of mapping?
Well, you have a shape, and then you have certain rules about which pieces will fit next to it. But there's certain freedom in that rule. You could put this one that way or another way, you see. And, you know, if it's a shape which very clearly has to fit that way next to it, then it just repeats, you see. But if there's some freedom as to what the next one will do, then you might have to make that choice, and certain choices will run you into difficulties later, and other choices maybe will allow you to continue.
Is there a relationship between that and what composers do with music? Because, I mean, there's a certain repeating determinacy in music, but obviously a composer just doesn't take a pattern and repeat it indefinitely. They take a pattern, and the pattern seems to allow for some choice in movement from that pattern forward.
Well, maybe, I don't know. I mean, what makes a piece of music into a good piece of music? I mean, I have no idea. That's a much deeper issue.
Well, we do know a bit about it. We know that if it's too simple and repetitive, your interest gets exhausted. Yes, exactly. It gets stale very rapidly.
Sure.
And then as it moves towards purely unpredictable, it becomes indistinguishable from noise. So there's some place in between there, and you could probably move on that place where you get some ultimately harmonious relationship of predictable form and, well, something like the play of novelty that seems to me to be analogous to that possibility of shifting the shapes in this tiling problem. I mean, I think music is tiling something.
Yeah.
It's a representational form.
Okay. No, there's probably some connection. It's just that music, I mean, there's so much more freedom as to what you do. You see, with these tiling shapes, it's forced on you that either it fits or it doesn't, you see. With music, it's much more subtle.
Right.
So I would hate to make too much of a comparison between the two.
Yeah. Fair enough. One more question along that line.
Yeah.
Now that triangle you made.
Yes.
Now, what's the relationship between those paradoxical forms and the tiling problem?
Not much.
Because they seem to be, there's a play of representation and image there. You know, one of the things I've been wondering, I looked at all your diverse contributions and I thought, wow, there's a lot of things happening in a lot of different places, but there's something that's not random. There's something at work that's a kind of a uniting principle that might be, I don't know, it might be the problem that you're trying to solve in some deepest way that's uniting all these elements of exploration and interest.
I don't know, you're asking too hard a question. I don't know. Sometimes I don't see any overriding principle. I mean, there's a sort of thing, something feels right. Now, why does it feel right? I mean, that could be something very subtle.
Yeah.
It may be wrong, too.
Oh, maybe
they are wrong.
Yes.
So
it seems to me that also is related in some important sense psychologically to that notion of understanding. The feeling that it's right. It's like, it's interesting that it can be wrong, but it's also interesting that it can be a predictor of, like I had a student, she was very creative, and she would come up with hypotheses that were damn good, but she was more creative than the typical psychologist, and I don't say that in a denigrating way. I mean, she was more like an artist than a researcher. And then what she would do is spend like 6 months writing out the algorithmic pathway to that conclusion, even though that is not how she derived it. But she had a pretty unerring ability to jump forward to the right place with her intuition. And it's something like a deep form of pattern recognition You don't need the full pattern to infer what the pattern might be. You can have a sparse representation of it, leap to what might be analogous to a tiling solution, I suppose. And that seems to be something related to the accuracy of intuition. I know when people become schizotypal, for example, and paranoid, that also happens in paranoia, they have a lot of intuitions about patterns that might be there, but most of them are wrong. And it's like their pattern recognition system has become, it's exceeded the limits of its capacity for accuracy and is starting to see pattern in what's truly random. Prediction error.
Yeah, well.
May I ask, there's I think one important distinction here, from what I can understand, Sir Roger, is what the nature of understanding is not to be simply reduced to belief or intuition, though it may be related to them. When one understands something, let's say that's the simple equation that 2 + 2 = 4, it's not a belief that is true. Understanding is operating at a level that is beyond belief. It has a certainty, an inner certainty that is not subject to doubt fundamentally. And what I was wondering if it might be helpful, just for the sake also of the people who may subsequently watch this conversation, if you would be willing, Sir Roger, to give us a sense of the way you describe the three spheres of matter and mind and mathematics, as that might give us a basis for some quite rich conversation subsequently.
Well, maybe. You want me to describe the picture? I mean,
please.
Well, this was just a way of thinking about the relationship between mathematics and the physical world and the world of conscious perception. And I was regarding each of these as a sort of world. I mean, whether that's a useful way or not, it was just helpful to me. And there is the mathematical world, and I take a very Platonic view here, that the mathematical world exists independently of us. And so when we find a mathematical result, it's more like a discovery than an invention. So it's there already, and you find it. So this is certainly a feeling that, as far as I'm aware, most mathematicians have. And the truths are there, and they're there independently of us. And if we're lucky, we can find one of these truths and see why it is a truth. Now, that's one thing. Now then there's the physical world. And the physical world, the more we learn about it, the more we find that it operates according to very precise mathematical laws. But yet it's very small. You see, if you look at a mathematical journal, you find it's almost entirely full of things which have nothing whatsoever to do with physical world. They're playing around with mathematics for its own sake. That part of the mathematical world, which actually does have direct relevance to the way that the physical world operates, is a small part of it. So I have a picture of this mathematical world, and a tiny bit of that comes and imposes itself, or whatever you like to explains, or whatever you like to say, the physical world. So the more we learn about the physical world, the more we see it is driven or acts according to these very specific, tiny part of the mathematical world. And the second thing is, in that physical world, which seems to be operating according to mathematics, there are entities which seem to be able to perceive and understand and have consciousness. So the acquisition of consciousness in whatever way is a small part. You see, the world consists of rocks and things like that, which don't seem to have any of this quality. But there are certain creatures, things, such as people in this room and elsewhere, and probably other animals, which may have less of it than humans, but on the other hand, I'd certainly think they have consciousness, some of them. So, but still, it's a tiny part of the physical world which seems to have access, or whatever the right thing is, seems to be able to be, in a certain sense, this world of consciousness. So it's again a small part of that. But there's only a tiny part of the conscious activity which is concerned with mathematics. So I had this picture which is sort of meant to be slightly paradoxical, that each world, in a certain sense, comes from a little bit of the world preceding it. And so it's drawn in a way which is like this impossible triangle, which is looks like a paradox. That's only a little joke in a way. I don't know how much depth there is to that. And I rather like to depict it in that way.
So so stop me when I'm wrong, okay?
Well, anyway.
All right. So it seems to me that the mathematical reality is something like the observation of the pattern regularity between things. It's not the things themselves.
Oh, the physical, which
Well, I'm thinking about the mathematical representation of the physical world. So, because there are things, obviously, but there are things in relationship to one another.
Yeah.
And the relationships between the things, like the pattern that your tiles compose, is just as real as the tiles.
Well,
Right? But it consists of the relationship between the tiles. And is it the representation of the relationship between things that's part of that mathematical world, rather than, I know it could be patterns
the
all the way
mathematical
down
world
in
is,
some sense.
you see that it's a physical thing. You know, it's just sitting in front of a mass building. So that's a physical thing. But it represents a mathematical idea, which only gives you the idea. It could say, oh, these tiles fit together in such and such a way, and these are parts of a Euclidean plane, and the Euclidean plane is a concept. We don't actually have it physically, but you can see, by looking at the tiles carefully enough and see how they fit together, that this is a mathematical thing you're looking at, in a way, and that this mathematical thing would allow you to continue, if you understand what's going on, indefinitely. So the entire Euclidean plane could be covered according to the rules of those shapes you see.
Okay, so let me ask you another question about that then. So, is the physical world one tiling solution to the plane of mathematical possibility?
I guess, in a sense. I mean, it's slightly... You see, it's not really talking about the laws of physics there. It's only in the sense that Euclidean geometry is a pretty good approximation. That's all it's saying. I mean, there's not much physics going on there. You might say, well, what makes these tiles, some of them shine and some not shine, or something like that? I mean, that's more like physics. But the actual design that's being used there, it's been put there by human beings according to what another human being said where they should lay them down. And that was driven by a certain mathematical concept. But it's different from the way that mathematics underlies the laws of physics. And that's quite different. It might be if you took one of those tiles and threw it across, or it would be pretty hard to do because they're quite heavy. But the way that would move in the air before it came down and crashed, that would be a clear indication of a physical law, the way in which gravitation behaves. And then the way the thing holds together, the law that makes these tiles solid, would be something to do with the quantum mechanics, to do with the ways that the atoms are constructed and how they connect with other atoms and what makes them solid rather than a fluid, or something like that. So that would be the way that mathematics drives the physics. It's general laws rather than a specific thing. I think that's
I'm
what I'm trying
curious
to say.
though, too, because in some sense, and I could obviously be wrong about this, but the physical reality seems to constrain the mathematical possibility, because there's only some mathematical rules that govern the behavior of actual objects, even though there's all sorts of possible mathematics that could govern the action of all sorts of hypothetical objects. Right? So imagine if there's an underlying, I can't help but think that this is associated with this many worlds idea, but if there's an underlying metaverse of mathematical possibility, you get the emergence of something like, well, what would you say, one concretized exploration of that possibility space, and that now establishes a relationship between one element of that mathematical possibility space, and well, in reality itself, doesn't exhaust the search space, but it seems to me that that's analogous to this tiling problem in some sense.
I think it's I don't know, I can't help saying I think it's really very different from what one is trying to do in mathematical physics. See, in mathematical physics, you're looking for general laws which seem individual instances of it agree with those laws, so that an object like one of the tiles that are being used outside math building, I mean, the trouble is that it depends on detailed laws about the atoms which construct the tiles and so, which has nothing to do with what we're talking about here. I don't think it is.
Well, I guess I was wondering partly because there's these fine-tuning arguments, and the question arises, well, there's lots of ways these phenomena could be interrelated, but in reality it turns out that there's a very finite and constrained number of ways that they are actually related, and those are the fundamental laws. And then the question arises, well, why that set of constraints and not some other set of constraints that seems equally probable statistically, if it was a sample of the mathematical domain?
Yeah, I guess I have to understand what you're saying a bit better. I mean, you could say, okay, there's this building, well, the one we're in now, which has in the front of it a certain tiling. I mean, if you're going to explain that, I mean, that's very different from what mathematical physicists do. I mean, they're just looking for general principles.
Right.
And as far as we're aware, those general principles are not violated in what's been going on in this building. However, that's not entirely what I would think, because what's going on in this building and so on is an implication of what's going on in people's heads. And this does have to do with consciousness. And what's going on in consciousness, in my view, is not yet part of current physics. So I'm trying to say that although we have very good theories about how things behave, bodies behave, they're not good enough yet to tell us how the conscious human brain operates.
So do you allow your imagination to wander into the domain of metaphysical speculation about that? I mean, because you're making a case.
Yeah.
I mean, I was talking to some divinity scholars the other day, and they were laughing, I suppose, about physicists who say, with regard to the Big Bang and the hypothetical emergence of everything out of nothing, that give us one free miracle and we'll proceed from there. And so, I mean, there is speculation among physicists that the laws of physics don't apply to whatever the state of existence was before the universe emerged into being. And you're making a case now as well that consciousness itself may not be able to be encapsulated within the realm of our current physical theories. So what do you think the metaphysical, or do you...
Let me try and get it. I'd have to unpack something here, because we're venturing on a different topic here.
Yes, I know.
Which is the question of the Big Bang.
Yes.
Which I have a different view on that from what you normally hear.
Okay.
So, but that's...
Well, that'd be fun to start
We can talk about that if you want to.
Yeah.
That's interesting topic to talk about. But that's really different. And as far as I don't even see a connection as things stand from what I'm worrying about in consciousness.
But what I'm worrying about, both stand outside the laws of known physics in some sense.
But let me say something else which outside the laws of known physics. And this is not something that people normally even recognize as a problem. I mean, they do, but they shove it under the carpet, which is what's known as the collapse of the wave function.
Mm-hmm. Mm-hmm.
Now, you see, current quantum mechanics, strictly speaking, is an inconsistent theory. That's a rather brutal way of saying what Einstein and Schrödinger and even Dirac said, that quantum mechanics is incomplete. And the way to explain this is, okay, there's a wonderful equation which tells you how a state evolves in quantum mechanics called the Schrödinger equation. Now, the Schrödinger equation tells you, if you know what the state of a system is now, the Schrödinger equation tells you what it will be tomorrow, if you like. The evolution of that state is governed by this wonderful equation due to Erwin Schrödinger. The trouble is that it doesn't. That's to say, the way physicists usually use the Schrödinger equation is to work out certain probabilities of what an observation on the system would tell you. So what you have to do is you wheel out of the cupboard a measuring device. In this measuring device, you set it on the system, which is evolving according to the Schrödinger equation, and it measures it. And the process of measurement does not follow the Schrödinger equation.
Right.
It gives you a probabilistic answer, this or this or this.
So that's another outside the system problem.
Well, it's certainly outside the Schrödinger equation.
Right.
And Schrödinger was terribly worried about this. I mean, he produced his cat in the box and all sorts of things. You see, he clearly realized there was a problem, as did Einstein. There's no question about that. Some others didn't. Well, they took a different view. They said, look, we don't understand the theory well enough. And that's more that we're saying. Where Schrödinger was not saying that. He was saying we understand it well enough to see that that's not the way the world operates. When you make a measurement on a system, it does not follow the Schrödinger equation. And that's what people understand about quantum mechanics. But it's a sort of vague set of rules about, it doesn't tell you what constitutes a measurement.
Right.
That's the trouble.
Right. Yeah, that's a big trouble.
That's
actually.
the big trouble.
Yeah.
They say if you do a measurement, then it just becomes probability for what this or that or the other. But it doesn't say what kind of a device makes a measurement. Now, there's one school of thought, which has been going on from way back to the early days of quantum mechanics. Wigner, in particular, promoted this point of view, that it's a conscious being observing the system, and that makes
that's what Wheeler believed, I believe.
I think Wheeler might have believed. Quite a lot of people believe that. I think von Neumann had a similar sort of view. I'm not quite so sure about his view, but certainly Wigner. And I talked to Wigner about this. Yeah. I got the feeling from Wigner he wasn't quite as dogmatic he was made out to be on this issue. He just thought this was a possibility, I think. But anyway, people often refer to it as the Wigner view, that it's a conscious being who makes a measurement. That's not my view. My view is that it's almost the opposite of that view, that there is an objective physical process which deviates from the Schrödinger equation, in which the state does collapse so that it becomes one or the other with certain probabilities. And that this has to do with when gravity is brought into the picture. And there's reasons for believing this. I don't want to go into that. But there is reason for seeing...
I'd like you to go into it, if you would be willing to, because I'm very...
Well, it's a very clear mathematical calculation. There's not a question about it. It's a question of what you do with it, you see. And what you do with it, according to me, is to say, okay, it tells you that this system has a lifetime, and it will, in that lifetime, become one or the other.
Without a measurement.
It's sort of... That's right, yes. Without a...
Well, it's so interesting to me
right.
that you're interested in consciousness, and you see that consciousness in this Gödel theorem sort of manner, and I would think the most predictable thing for you to believe as a consequence of that would be that it is conscious measurement that collapses the quantum indeterminacy, the waveform, and yet you don't. You think that that statistical vagueness will collapse into something that's essentially, is it either or, is it binary?
Well,
is it 0-1, the collapse?
No, you mean no, there's a probability it'll do one
Right,
or the other. Yeah,
right, but when the probability collapses...
Well, if it's a two-state system, you see, you might have an object which is in a superposition of here and here.
Yeah.
That was Dirac's first lecture, I remember hearing that, and he took out his piece of chalk and said, well, and he was talking about atoms, you see. According to quantum mechanics, or a particle, so a quantum particle can be here, or it can be here, or it can be in a state which is partly here and partly here at the same time.
Right.
And then he took out a piece of chalk, and people tell me he used to break it in two. I can't quite remember, because my mind was drifting away from what he was saying, and I was looking out of the window and thinking about something completely different. And unfortunately, it only came back after he'd gone on to the next topic. So I missed the explanation, which was probably a good thing, as I think back on it, because probably the explanation was something sort of to calm you down and stop worrying about the problem. I suspect it was something like that.
So you don't think that a conscious observer per se is necessary to collapse the waveform?
Absolutely. That is what I'm agreeing with you.
Yeah.
I don't believe that, yes.
But you do think that, if I'm not mistaken, that the presence of an observer in the universe, that is to say, or the observation of the universe by us, is that true to say, is fundamental to the universe?
Not really. That's an interesting question, but it's not part of my view. The world would be there quite independently of whether there were creatures of consciousness
yes,
walking around on them.
yes.
So can I ask you a question about that? So it's related to this. So it's my understanding, and I could be wrong about this too, because I'm way afield here. I'm out of my depth and area of specialization. But my understanding is that, in some sense, as far as a photon is concerned, that the universe is two-dimensional, perpendicular to its direction of travel.
I don't see that, no, but go on.
Well, I thought that this, it's a consequence of the contraction of things as the speed of light is approached, and so.
Oh, I see. No. That's. You're talking about the Lorentz contraction or whatever.
Yeah. Well, and
No.
I thought, as part of that part of the reason that no amount of energy can propel something past the speed of light is because, in some sense, the light beam is already where it is and at its destination at the same time, and you can't get flatter than flat. Now, the reason I asked you that, though, was because it pertained to this other question, which was, if you could imagine what the universe might be like phenomenally from the perspective of a light photon, that's very unlike the universe that we perceive.
Oh, I see. I mean, if you were riding on, Einstein used to talk
Yes,
about
I know.
riding on a light. The trouble is that you can't sit on a light.
Yes, that is a problem.
But if you were nearly going, very, very fast like that, the passage of time, you would think it hadn't taken any time at all.
Right. And that's the same as being at the starting point and the destination at the same. Yes. Okay. Okay. So now for us, we perceive things with duration and distance, and so but the photon is in the universe and we're in the universe, but the universe looks very unlike each of those situational positions. And so you said that there would be a reality independent of consciousness, but I'm curious, when you think of a reality independent of consciousness, what are the attributes of that reality? Like, is it a field of quantum potential? Is it?
I'm not quite sure I understand the question, but I mean, classically, there's no problem. I mean, this thing about the contraction and all that stuff with us going close to the speed of light and so on, this is classical physics, so we're not worrying really about the problems of quantum mechanics there. But they're already there in classical physics. But if you had a particle traveling at the speed of light, let's say just less than the speed of light, and if you could sit on that particle, it would seem as though you got to your destination almost instantaneously. That's correct. But that has nothing to do with quantum, well, not directly to do with quantum mechanics.
Right.
That's relativity. Yeah.
Right.
Yes, sure.
But
Okay.
the phenomenal universe at that speed is radically different than the phenomenal universe at our speed.
Yeah, but the universe is there. It's just a question of, I'm not quite sure I understand this. You see,
Well, I'm trying to understand how it can be all of those things simultaneously, like,
no,
and what that means.
That's not a problem. It's just, when I say it's not a problem, what I mean is that there is a way of looking at relativity, which means special and general relativity, which is completely coherent and doesn't really worry about who measures what. It's just there. You have a space-time, which is this four-dimensional structure. Maybe hard to understand and visualize and so on, sure. But it's the thing which is there. People call it a block universe view.
Well, I think about it as a whole symphony at once, in some sense.
Well, if you like. But it's all there. And what something measures in that system, you have to go and ask the question. If you had a body traveling with a great speed and there was a clock on that body, you'd ask for how many ticks does it happen before one end and the other. That's perfectly well defined. If it was sitting stationary, You would have so many ticks between starting and finishing. You could have one which goes out and comes back. You might say there are only about 4 ticks, whereas this one had 1,000 ticks. Well, that's the answer. It doesn't mean that time is...
So it's susceptible to all those interpretations simultaneously.
Yeah, because each one is just, it's only measuring it with, it carries the clock with it, and that clock ticks at a certain rate, and that's fine. There's no problem. When I say there's no problem, I mean it's not a philosophical problem. There's a little bit of a problem of getting used to the ideas, sure. No, I agree with that.
Yeah.
But that's not the issue. You can, once you've got used to the ideas, and you can see time is something which depends on how you're moving.
Right.
And the clock which is moving fast.
Is there any difference between that statement and rate of change depends on how fast you're moving? Like, is there any difference between time and rate of change?
But rate of change is...
Because I think of time as the averaged rate of change. And so when you say that time slows down as you move faster, you're not saying much more than as you move faster,
That's just a question. You see, I think the mistake here is to think of time as an objective thing.
Yes.
Which is attached to this model, and it's
right.
not.
Right.
There is no concept of when such an event happens. You might say, oh, well, is this event later than that event? Well, if they're what's called space-like separated, that is to say, you'd have to go faster than light to get from one to the other, it's a meaningless statement because there is no universal concept of time in this model.
Right.
It's just not there. I think, you see, that goes against what we normally feel about time.
Yes.
We think about time as progressing and somebody on the Andromeda galaxy.
Well, we experience duration, so...
Yes, but you see, what about when is now? I often use this, I think I use this example of 2 people crossing the street. And they're just walking speed, crossing the street. And the question is, according to one of these people, there is at the same time as they cross each other, there is an event on the Andromeda galaxy where a space fleet has been launched and they're going to invade the Earth. According to the other one, the decision has not even been made yet as to whether they're going to invade the Earth or not. Now, this is only because you're trying to transfer your local notion of what you mean by time to the Andromeda galaxy. Mm-hmm. And this depends on what frame you're using. So if you're using a one moving frame, it hasn't happened yet, and the other one, it has. You just have to get used to that idea, that there is no universal notion of time ticking away
independently of frame of reference.
Yeah, that's right.
Yeah,
yes.
Okay.
So we get used to that.
Can I go
idea,
sideways one more time?
Okay,
Because
yeah,
I'd like to ask you, like I said, I've been wanting to talk to a theoretical physicist for like forever. I'm really curious about black holes. And so I have this idea. So tell me what you think about this. So when a star collapses past the neutron stage into a singularity, and let's say there's multiple black holes, mm-hmm. Are they all the same singularity?
Oh, no.
Okay.
Well, I mean, you can link up them somewhere, but no, we don't. Apart from saying we don't know, I would say no, they're different singularities.
Well, I was trying
to close that statement, and we don't really know what we're talking about here. But go on.
Okay. Well, I thought about this. Partly, God, it was so long ago that I thought about this that I can hardly even remember what I thought. But I was trying to wrestle with the fact that you get this unbelievably intense, not even single point gravitational field, and there are strange effects of time inside the event horizon of a black hole from the perspective of an observer. Now, if I remember correctly, if you were watching someone descend into a black hole from outside, don't they go slower and slower?
Yeah, you would see them hovering on the horizon and then fading away very quickly, actually.
Okay.
They would just fade, yeah.
They would fade. What happens to their sense of time once they pass the event horizon compared to the sense of time, the framework?
Well, they would go right through and they wouldn't notice anything at the horizon.
Right, and what would that look? And you wouldn't be able to see them
anymore. That's a very big black hole.
Yeah.
As a little one, they would have been wrecked by the tidal forces. But yeah, if it's a big enough black hole, you could imagine going through it. You wouldn't even know you'd gone through the horizon.
If you could see someone descending into it, how long would it take them to arrive at the surface? Is that forever?
Not for them, no. They're just
No,
happens
but
to-
for you watching them.
Well, you just see them. You don't ever see inside the horizon. The light can't get out from inside the horizon.
Right.
So you never see that. That's right. So they could be watching their watches and thinking, whoops, we've gone through now. And they would do that. But if you could see their watch from outside, you'd see the hand slowing down and getting closer and closer to the moment when they cross the horizon. But fading out at the
But
same
it would
time.
be slowing down.
Yes. You'd see it slowing down, yes.
Okay, then if you could see inside, would you see that continuing to slow?
No. Sorry, I'm not sure what you mean
Well-
by seeing inside.
Once they pass the event horizon, you can't see them anymore.
That's
But as
right.
they approach the event horizon, if you were watching them, you'd see their clock slowing.
Yes.
So
if you're outside.
If
yes.
you're outside.
Yeah.
So then I'm wondering, you can't tell this, but their clock is going to slow the same way as they continue moving towards the black hole. And
So
then
that's the trouble, you see, it's the wrong way to think of it.
Okay.
That their clock is there a time which their clock registers? That's going to saying there is a universal time which everybody
Right.
is supposed to respect in some sense. Relativity says no. There is no notion of
But I'm
universal
assuming
time.
their clock would continue to slow relative to you. I'm not trying to assume an absolute time in the question. I'm wondering is that as they approach, I know, the problem that you can't detect it is the problem here, but as they're moving towards the star relative to someone who's watching them, their clocks are slowing.
According to
This frame of reference.
signals that you would receive, maybe that clock, it emits a little flash of light.
Yeah,
every second,
yes,
like
that, exactly.
And you see, look, those flashes light are slowing down, and
Getting farther apart.
yes, that's right.
Okay, so then, from the external perspective, I was thinking that it would take them forever to reach the singularity. And if it takes forever, then that would be the same amount of time that it would take everything in the universe to collapse back into the initial singularity if the collapsing universe theory is correct. And so the reason there's infinite gravitation in some sense at the point of the singularity is because that's a point at which the end of the universe is already manifest in the current universe. And that seems to me that would be, what would you say, in keeping with the idea in some sense of a block universe.
So I'm not quite sure I see the problem here. You're thinking about the whole universe, a collapsing model.
Yes.
Which you could certainly
Yes,
have.
and I'm also wondering if that's a model that you think is...
No, it's not my model.
It's
But
not,
it's certainly a
okay.
model that people can consider, sure. And you might have an entire universe which is collapsing inwards, yes. And then you would hit the singularity before you see somebody else hitting it. In those models, you would find you're in trouble and that your curvature is getting too big and you'd be killed by it. As you were watching somebody else and you see, no, they're happily not nearly there yet.
Right, not nearly there yet.
So
yes.
that's what you would-
Yeah,
that's what you would
That
say,
is what
yes,
you...
yes.
Okay,
Yeah.
that's okay. All right, then your model isn't... is it a Big Bang model with an initial emergence out of nothing and then eventually a collapse back to that?
No.
No, so, okay, so how do you conceptualize that?
Well, first of all, it is a Big Bang model. In other words, there is a Big Bang, but the Big Bang was not the beginning. The model, the reason people have trouble with this model, I think, is you're probably going to have trouble with it, and you're not unique in this. You see, people tend to think that if you have a model in which it keeps on going in some sense, and your Big Bang is not the beginning, that you've got to collapse back. So it expands and then it comes back, and then you're back with... But
It
this
seems
model
simpler that way.
Yes, but this model is not like that. And that's where you've got to get your mind around it.
Okay.
And people have trouble, and I agree with it. It is a crazy idea, and I admit it's a crazy idea. The trouble is, it seems it's quite likely it's true from certain
Okay.
observational things. But it's crazy too. It can be crazy and true at the same time.
Yeah, that's like a definition of life.
Yes. But you see, in this model, the universe expands and it expands, and this exponential expansion we seem to see, the stars seem to be starting to go away from us, these very distant stars that people look at, with an increasing speed.
Right,
and
right.
it seems to be this exponential expansion. And
That's
I
what's
agree with
driven the
it.
dark energy hypothesis, I
That's
presume.
what they call it's really well. I claim it is absolutely nothing inconsistent with Einstein's 1917, was it, in modification of his, that he regarded his biggest mistake, but is probably actually right. That's to say, the introduction of a cosmological
Constant. Right. Yeah.
He introduced it for the wrong reason. That's true, but he was right to introduce it, even though he regarded his biggest mistake. There's a real
Well, he needed it to make things work, but he didn't have any real practical reason for assuming that it was true, apart from...
He wanted a static universe. He didn't like the expansion. No, he didn't. No, this was a time before. I think Hubble had already seen the expansion, but it hadn't quite got through to Einstein how convincing these results were. So he wanted a universe which was just static and stayed there forever.
Right.
And then he needed the cosmological constant to do that. That's correct. He would need that. However, he was wrong. When he got convinced, oh no, the universe is expanding. Sorry, he said, oh, well, that was a mistake. My biggest blunder, he said. The trouble is, his biggest blunder turned out to be true. Apparently. I mean, this is an argument. People don't necessarily think it was. People might not think it's the cosmological constant. I think it was. I think it's right. I have reason, internal reasons for that. But let's say that this is right. It's a cosmological constant. The universe expands and expands, exponential expansion. Now you might ask, who's in this universe eventually? Not us. The black holes will all have evaporated away by Hawking evaporation. They've swallowed galactic clusters. What's left in the universe? Pretty well photons. Now I'm giving you the simplified version of the theory because there's some questions about it still. But let's say it's dominated by photons, which is pretty well true, but not. Let's take that.
Okay.
Now the trouble with photons is that they don't feel the passage of time.
Right.
And more importantly, the equations governing light are the wonderful equations due to James Clerk Maxwell, the Maxwell equations. And the Maxwell equations have a very interesting property, that they can't tell big from small. They're what's called conformally invariant. That if you have a system in which you've got some electromagnetic field, and you could stretch this system to bigger or smaller, it doesn't notice the difference. The equations work just as well. And you can squash them here and stretch them here.
Well, is that in part because space really doesn't mean anything to a photon?
In a sense. Well, it's the scale of space. You see, it's what we call, there's a term which I'll use here, it's called conformal. Conformal means big and small. I very much like, we talked about Escher a minute ago, there are these Escher pictures called circle limits, where he describes what's called hyperbolic geometry, but don't worry about that. The most famous one is these angels and devils. And you see there's a circular boundary, and they look as though they get smaller and smaller and smaller as they get to the edge.
Yes.
Now, as far as those angels and devils are concerned, the little ones are just the same as the big ones.
Right.
They don't know that they're smaller towards the edge, and that to them is an infinite universe. But to us, we can see, no, there's this infinity which is just sitting there. And these angels and devils, if they don't know big from small, I'm not sure, I have a bit of trouble using this to explain things because the angels and devils do have a size in the picture. But you see, if they were made of massless material, that wouldn't know big from small. So if they were made of just electromagnetism, then big and small are equivalent. And so you wouldn't know when you got to the edge of this universe. So that infinity is just like anywhere else. That's the difficult concept in this thing, that the photons reach infinity without realizing anything funny has happened, if you put it like that. Infinity in this conformal picture is just like anywhere else. It's only mass that knows the difference. If you want to build a clock, you need mass. And this comes from the two most famous equations of 20th century physics. And the two most famous equations, one of them is Einstein's E equals mc squared, of course, which tells us that energy and mass are equivalent. And the earlier one was Max Planck's E equals h nu, or E equals hf, whatever like you call the frequency, which tells you that energy and frequency are equivalent. Put the two together, that tells you mass and frequency are equivalent. So that means that if you have a mass, it is a clock. It has a frequency simply determined by its mass. And this fact is really the basis of modern clocks, which are extraordinarily precise. They don't directly give this because the frequency is much too high. You have to scale it down. But roughly it's the same idea. So a mass is a clock. But the other side of that coin is if you don't have any mass, you don't have any clocks.
So you don't have any time.
You don't have any time scale. You don't have any distance measure. So if the world is inhabited only by massless things, say photons, then it doesn't know big from small. It doesn't know hot from cold. And so the idea is, and this is where you have to take a deep breath, the idea is,
as opposed to all the other parts of this conversation.
yes, the idea is that the remote future is indistinguishable from a Big Bang, so long as there is no mass around. Now, the remote future, the reason you have no mass around is basically, listen, there's a complicated part of the argument, but let's say it's because there's mainly photons. That's good enough. What about the other end? What about the Big Bang? Well, there's lots of mass there, surely. But the thing is that at the Big Bang, things get so hot, things are moving around so fast, if you like, that the energy, or the mass energy, mass-energy, the concept of mass, according to Einstein, is almost entirely in their motion. And that the mass becomes more and more irrelevant the closer you get to the Big Bang. So again, you have a situation where mass is effectively zero. And
So is it your claim, belief, theory, that when things ground out in a universe that only consists of electromagnetic radiation, that is now a precondition for an event like the Big Bang?
In a sense, yes. I'm saying that the physics which is going on at the very remote future is extraordinarily like the physics going on at the very beginning.
I'm going to end there.
When I say beginning, I only mean the Big Bang, because it's not really the beginning.
Yes, yes. Yeah. Well, it's such a lovely place to end, and we have been going for an hour and a half, and I don't want to wear you to a frazzle.
I'm not frazzled.
Well, I think I might be.
Do you mind if I just ask a couple of questions?
Go ahead,
Jordan?
Stephen, please.
One of the things that I'm very struck by in your account of the three realms of matter, mind, and mathematics, roughly speaking, is that the realm of mind or consciousness is the realms are not reducible one to another. So the realm of mind cannot be reduced simply to the realm of matter, nor can the realm of mathematics be reduced simply to the realm of matter.
They each have their own existence. Well, you see, it's a picture which I've used. I'm not sure whether it completely concurs with my current views, but go on with what you're saying.
What I wanted to ask you about is, and it's a two-part question, but I'll start with the first here, and that is that what is the relationship? It appears as though there's a fundamental intrinsic relationship between the realm of our consciousness, our thinking, on the one hand, and the realm of mathematics, or let's say intelligible reality. That I'd like to hear you comment on. I mean, just to maybe see this a little bit. The philosopher Plato, as you well know, and you often describe this realm of mathematics as a Platonic realm, it had a theory of recollection, and we can regard that as a myth or whatever, but it does appear at some very profound level that it's true that we couldn't come to understand things that have an intelligible reality, like mathematics, if they were not already somehow in us, or potentially in us, in the patterns or structures of our own consciousness. So I'm wondering if you could say a few words about the relationship between our thinking, or the realization of our thinking, its development, and the realm of the mathematical, or more broadly speaking, you might call it intelligible reality, or however you might want to construe that realm.
Are we talking about the perception of mathematics, or I think
Let's start with that. Yes,
the possibility of understanding mathematics.
Yes, the possibility of understanding mathematics.
Gosh. So what? I've lost the thread of the question.
The question is, do you believe there is there an intrinsic relationship, that appears to be, between our thinking, the realm of consciousness, and the realm of mathematics, or intelligible reality, independent of us, but intrinsically related? Are those realms intrinsically related?
Well, I think I'm trying to say that we can access the truths of mathematics with our consciousness. How we do that, I don't know. But somehow we can access that world. And of course, some people find it easier than others, and this is a difficulty in trying to talk about these things.
It's a question for Richard Dawkins later in the day.
Yes, and at the risk of going out too far, I want to just make an effort at relating this question to the work of Dr. Peterson. One of the things that Dr. Peterson has clearly shown is that there are many people who are not. It's called for some people, as a shorthand, we call this the meaning crisis. Many people who are finding they simply don't have the resources to make sense of their lives in a way that seems to be adequate to the demands of their own self-consciousness. And so, at the heart of human life, as evolved, as creatures that are evolved as self-conscious, is clearly finding a way of understanding ourselves in the world that is adequate to the demands of that very self-consciousness. And life has what life is as meaningful is precisely to answer that demand of ourselves as a self-conscious creature. And one of the things that it seems to me that very much is at work at this, at least some profound level, is the idea that everything is reducible simply to materiality, that, as it were, eliminates any substantial reality to our own consciousness. If that were true, it would just be an epiphenomenon. But it also denies the existence of an independent realm of spirit, as some philosophers would say, or of intelligible reality, or simply put it in terms of the mathematical. And so what I'm wondering about, and it's maybe an outrageous question to ask a physicist, but you have written many beautiful books that are clearly related very much to this very question, that has to do with the nature of human realization. That is, say, how we come to understand ourselves in the world. And what I'm trying to drive to here is whether you have thoughts on the nature of the realization of our consciousness. We could call that simply human realization as a shorthand, and about
it's a question like what might constitute the fact of intelligibility, right? There's a capacity for us to reflect this structure, that the mathematical structure, the physical structure, and that seems to be part of what you described as understanding. It's like perhaps you're formulating a question about the metaphysics of that intelligibility.
Yes, or we could simply say, Sir Roger, in your observation and reflection, what are the forms of life and culture that appear to facilitate that deep human realization, that appears to have a intrinsic relationship between ourselves as self-conscious creatures and the nature of what is independent of us. And that does seem to be at the heart of the question of meaning that Dr. Peterson has been working on and perhaps helped others to think about.
I mean, I'm not quite sure I've grasped the question here, but it has to do with this relationship between conscious beings and this world of mathematical, Platonic world, if you like.
Yes.
And it's certainly something which people differ very much in how easily they make that contact, if you like. And I certainly have made attempts to try and explain to people who are not used to thinking about mathematics, if you like, to gain a little bit in that understanding of what's going on in mathematics. So that's how successful or not, I don't know, but it's at least an attempt to.
Well, thank you. And
yes.
As a follow-up to that question, do you intuit or think or believe that in that realm of the mathematics, as you might say, intelligible reality, do you think other things might also be included in that? Let's say truth generally, or love, or beauty, because of course the dominant view right now is that these are simply constructs of the human mind or culture, or it's another way of saying the human mind, or material forces that are at work that have given rise to these constructs but don't actually have any independent reality themselves. Do you think that there is a kinship, or perhaps that mathematical reality or truth is part of a realm that exists as independently as mathematics do?
I think that I believe I have in some places, I'd have to think where it is, adorned this picture with the Platonic world being part of a bigger picture, which has to do with other things than, you see, that's to do with truth, if you like, but there's a question of beauty or other qualities. And I think that may be relating to the question you're raising here. I don't have much to say about it, but I do remember drawing a picture somewhere, I can't even remember where now, in which this Platonic world was part of a larger body of things like beauty, for example, and qualities, or virtue, in fact, also, qualities which are things that our consciousness is concerned with, and very important. But not quite what I've been talking about, which is a very specific thing, which is understanding mathematical truth.
Yes.
So I certainly would agree that there's more to it than that, and I think that's what you're telling me. And I'm going along with that. It's just that I didn't know what to do with it. I think that's the trouble. Yes.
Well, the reason I ask is because it does seem to me that if these two things are connected, that is, say, the nature of what we are and think that we are is somehow intrinsically, according to its own, let's say, structure or nature, connected. I mean, we might even say, if human beings don't have no nature, there's some sense in which mathematics itself is not even possible. I mean, certainly not for us. I mean, it seems to be we have an innate capacity, to varying degrees, as you say, to think these thoughts or perceive these realities. But if that realm is, say, the realm of mathematics is part of a larger realm in the way that you've just said, and it is related intrinsically to what we are, that our self-perception and self-consciousness has a structure such that it calls out for, in some sense, an understanding of these things, or an understanding of ourselves in relation to those realities. It does seem to me that human realization has to be thought very fundamentally through from that starting point.
Yeah, well, I think all I can say here is that I have considered that in places. I could probably find a transparency that I used to use for talks. Whether I can find a place in something I've written, I'm not so sure. But I certainly did consider the Platonic, truth, if you like. It was really more like truth, beauty, and morality.
In that order.
That's a good question. I think I'm going to see if I can find whether there was an order.
And
I think there was an order.
What would, and when you say morality in that sense, truth and beauty, in some sense, that's more apprehensible than morality. Do you have any idea why your intuition drove you to place morality at the outermost part of that particular diagram?
I can't remember whether even I did or not.
Okay.
So that I'd have to rake through all the things I'd I suspect there must be an article somewhere where I did that, but I do remember using it in talks. Yes.
Mm-hmm.
So this would be addressing the remark you made. It's more that I don't really have anything that I can say. I can say, okay, I like things. I like Bach, for instance. Very fond of that very much, and that certain. I think particularly with music, there are things which I can relate to very much. But in order to make it anything that I can talk in a rational way about, I give up there because I'm not good enough at arguing about these things.
Right.
Yeah.
Oh, I guess we're doing this
that
way.
way.
I'm so happy that you agreed to talk to me.
Well, I hope it was of some use to you. Yes. But some of these things
I think that's
are
fair
difficult to describe, and clearly it's particularly these things with the Big Bang and all that, which is an idea which we do seem to see evidence for something. Signals. You see, there could be signals coming through from the previous eon, as I call it, and I think we see them. The colleagues of mine.
You'd have to throw that in at the end, wouldn't you?
Well,
what do you mean?
Oh, well, they've been. You see, I used to go around giving talks about this stuff very often. I thought, this is fine, I can do this. Nobody will ever know whether I'm wrong or not, and so I can talk about this forever. And I thought, I wonder if that's right. And I thought, well, first thing I thought about was collisions between supermassive black holes. I mean, our galaxy is in a collision course with the Andromeda galaxy. It has a black hole much bigger than ours. After we collide and things settle down a bit, our poor little black hole will be gulped down by it. And there will be enormous gravitational waves going out, carrying away some significant proportion of the mass energy in the two objects being concerned here. And maybe they could be detected by different people. Maybe they could be detected in the next eon. Gravitational waves can get through from one to the next. This is clearly, according to the model, they can. So various people tried to search for these things, mainly my colleague Vahe Gurzajan, who is an Armenian, and some other Polish people who later get on it. And they had a much clearer calculation of what they regarded as the probability that these signals were really there. A 99.4% confidence level, I think they got.
That they are?
Yes, that they're there. Some people didn't believe us because they don't believe the model, of course. But then more importantly, more recently, this is a paper, mainly one which came out in the monthly notices of the Royal Astronomical Society about a year and a half ago. And we claim that we see what we call Hawking points. That would be after one of these galactic clusters gets swallowed up by a black hole and there's nothing left but this black hole, it evaporates away by Hawking evaporation. Mm-hmm. All that radiation doesn't even begin until so late that by the time it comes into the next eon, it's a little tiny point. That little tiny point over 380,000 years spreads out. There's a little bit of an argument about how far it spreads out, but what we seem to see is it spreads out to about 4 degrees across, which is about 8 times the diameter of the full moon. And that's what we see. So we see with now a bigger confidence level, 99.98. There is an argument now which is to do with whether the actual size we see is consistent with expectations, and there's interesting questions about that. But ignoring that point, we have a 99.98% confidence level that they're there. The spots, there's little spots of raised temperature, and we see them. And why are they there? What are they doing there? According to current theory, they shouldn't be there. According to the theme I put forward, yes, they should be there. And they're the result of the remote future of a galactic cluster.
Propagating itself into the next eon.
The radiation, yes, it's the radiation, the Hawking radiation probably, which comes from the black hole, and all this mass gets concentrated into that and that comes through a little tiny point, which by the time you see it, is spread out to about 8 times the diameter of the moon. And we see these spots. And they're seen both in the more sophisticated Planck satellite data, and if you look at the, the 5 strongest points in the Planck data, and look in the earlier WMAP, that's a different satellite, completely different, and you find these spots exactly the same places in the WMAP data. There's a 6th one in the WMAP data, which is just about as strong as those 5. Look back in the Planck data, and that's there too. So those 6 points, I claim, are genuine Hawking points, as I'm calling them. And there's no other explanation for them that I know of. They're seen, and they are independently confirmed by another group who were claiming they don't see anything, but they do see they see evidence for these spots too. You just look at the data. Okay, what's the reason for it? Any current cosmology? I can't see any explanation for them. This model predicts them. I haven't seen any response from after a year and a half from the established cosmology community, published in a very respectable journal. It's probably the leading journal for astrophysical processes. There is an error, but in this, which is rather curious, but I don't want to go into that. But it doesn't much. Whether the confidence level should be reduced a bit, I think that's probably a case for that, but not much, because the signal is pretty strong.
Thank you very much. That was